In this video, we're going to look at the noise analysis of op-amp circuits and see how to design op-amps to meet noise specifications. We're going to focus on single-stage op-amps, although the results can be applied to two-stage op-amps, especially when the input stage noise dominates. We're going to start by doing a noise analysis for the simplest type of op-amp circuit, the simple actively loaded differential pair. You'll see that for all 5 transistors here, we've adopted the gate-referred noise model, where a single noisy voltage source in the gate of each transistor captures both the flicker and thermal noise. We're going to also at first focus on thermal noise specifically. This gate-referred voltage noise model is usable in this case because for all 5 transistors, we are assuming that the gates are connected to voltage sources with relatively low output impedances. So, for example, whatever bias circuit is supplying the gate voltage to Q5, Q3, and Q4 is assumed to have a relatively low source impedance, and same for whatever is driving the inputs, Vin plus and Vin minus. So adopting this model, first thing to notice is that the noise due to Q5 is split equally between Q1 and Q2. That is, the noisy drain current that results goes half into Q1 and half into Q2, assuming symmetry in the circuit, that is, matching between Q1, Q2, and Q3, Q4. Because of that, and considering that we're looking at the output of this differential pair differentially between VNO plus and VNO minus, then it's safe to assume that all the noise from Q5 results in zero differential signal between these two nodes. So we need not consider noise from Q5 in our analysis further. Then we've got just noise contributors from Q3, Q4, and Q1, Q2. VN1 and VN2 get amplified by GM1, which we assume is equal to GM2, and turned into a noise current. That then gets multiplied by the output resistance, which we're denoting RO in this case, and is assumed to be equal on both half circuits. So, moreover, we assume that VN1 and VN2 are the same. So each sees the same gain, GM1 times RO, and since there's 2 of them, we add together their power spectra with the factor 2 here. Similarly, the noise arising from Q3 and Q4, this is Q1 and 2, and the noise from Q3 and 4 is assumed to be the same, have the same noise spectral density, and they're multiplied by their own transconductances, GM34, n times the same output resistance. And again, there's 2 such transistors, so we've got the factor 2 here. So this then is the output noise spectrum. It has 4 terms, 1 from each of the 4 transistors, Q1, 2, 3, 4. We can input refer this by dividing by the gain of the amplifier. So the input referred VNEQ noise spectral density is VNO squared divided by the gain of the stage squared, that is divided by GM of the diff pair transistors times RO all squared. And that's what we've done here. And you end up with a lot of cancellation happening. And you see, first of all, that the input referred noise contribution of Q1 and Q2 is simply the gate referred voltage noise spectral densities VN1 and VN2. This isn't surprising because those noisy voltage sources are already connected directly in series with the input voltages. Second term here is the noise arising due to the active load transistors Q3 and Q4. And you see those gate referred noise voltages are multiplied by their small signal GM, GM3, and then divided by GM of the input pair, GM1, in order to input refer them. We can go ahead and substitute in the thermal noise of transistors Q1 and Q2. Recall that the thermal noise of a transistor is 4 kT gamma, and gate referred, it's divided by GM. So just a reminder there. And substituting that in, you get the final expression shown here. And again, we're neglecting flicker noise for now. So you get an interesting result, which is that assuming all transistors are biased with the same drain current, which they should be, assuming good matching, um, you're likely to have the input transistors noise dominant, assuming GM1 is greater than GM3. That is, that the input pair transistors have a larger small signal transconductance than the active load. Now, we're probably motivated to ensure that the input pair transistors have the largest possible transconductance, small signal transconductance GM for a given bias current, because that GM1 is also related to the unity gain bandwidth of the op amp and other things that may be desirable, its gain. So, so for that reason, we can expect that GM1 is probably among the largest small signal transconductances in the whole circuit. So we're motivated then to make sure that GM3 and GM4 have a smaller GM than the input pair transistors. That's why we will often bias the active load transistors with a relatively large value of V effective, so that for the same drain current they'll have less transconductance, whereas the input pair transistors would be probably biased with a low V effective, which gives them, for a fixed bias current, the largest possible transconductance. So again, this both maximizes the gain, the bandwidth, and minimizes the noise contribution of the input diff pair, while at the same time minimizing the noise contribution of Q3 and Q4 without negatively affecting the gain or bandwidth of the stage. So in summary, to ensure low noise from the stage while maintaining high bandwidth and high gain, we would seek to ensure that the input pair transistors have a larger transconductance than the active load devices, and the tail current transistor doesn't contribute much noise at all. If we design that properly, then the input referred noise of this stage is dominated by the input pair transistors, and if we neglect flicker noise, we've simply got the thermal noise term shown here. The factor of 2 arises because there's 2 input pair transistors with uncorrelated noise. Having analyzed the thermal noise of this stage, let's now focus on the 1/f noise, also called flicker noise. Again, Q5 contributes no noise because the assumption is that the circuit is symmetric and flicker noise splits evenly between the two half circuits. The noise of the input pair transistors is already input referred, so it shows up directly in the expression for input referred noise spectral density, whereas the flicker noise of the active load transistors Q3 and Q4 has to be input referred. First, it's multiplied by its W/L ratio and its carrier mobility mu(n), and then it's divided by the aspect ratio and carrier mobility of the input pair transistors Q1 and Q2. So if we substitute in the flicker noise spectrum for VN1 and VN3, you end up with the expression shown over here. Now you'll notice that if all 4 transistors have the same gate length, that is that L1 equals L3, then it's quite likely in this circuit that the active load transistors will dominate the flicker noise. The reason is because the flicker noise constants, K1 and K3, are different for NMOS and PMOS technology devices in a given technology. And generally, the flicker noise constant for NMOS transistors is larger. Moreover, carrier mobilities are generally larger for electrons than they are for holes, although this is less true in more advanced CMOS technologies. Now, we can reduce the impact of flicker noise from Q3 and Q4 by increasing their size, so we can keep their aspect ratio the same and therefore not impact their GM, but simply increase both L3 and W3 in proportion. Doing so would reduce the flicker noise contribution of the active load transistors, but because we've made these transistors so much larger, there'd be larger parasitic capacitances at the output nodes, and so it's quite likely we would negatively impact the bandwidth of this stage by doing that. So there's a noise bandwidth trade-off at play there. The second point here is that, as before, we would try and make W1 as large as possible, putting the input pair transistors on the verge of subthreshold, minimizing V effective, and giving them the largest possible small signal transconductance, GM, for the given bias current. This serves to reduce both thermal and flicker noise. That shows up in these expressions here because we see W1 in the denominator of both terms. And that's because all the noise sources at the output have to be input referred by dividing by the small signal transconductance of the input pair GM1. Now, although that analysis was for a simple actively loaded differential pair, a lot of the same results are applicable to more complicated single-stage amplifiers. For example, the folded cascode OTA is shown here. Now, we've already seen for single-ended cascode gain stages that cascode transistors do not contribute significantly to the output noise. The thermal noise current basically just circulates and doesn't induce a large voltage change at the output. Since the differential pair at the input is likely designed to have the largest small signal GM of all transistors in the circuit, it's most likely that their thermal noise will dominate the circuit's input referred noise. So we can make a simplifying assumption here, which is that the input referred noise of the overall stage is dominated by only the input pair transistor's thermal noise. This is based on the same assumptions that we made for the single actively loaded diff pair stage, namely that Q1 and Q2 have a larger GM than the active load transistors, and at the same time, the addition of the cascode transistors, Q5 through Q8, has very little impact on the noise at the stage. Other transistors here, such as Q12 and Q13, are off under normal operation anyway, and so they also contribute no additional noise. So as with any amplifier stage, a complete noise model must include both input-referred voltage noise source and current noise sources. So here's a general op-amp noise model showing both the voltage and current input-referred noise sources. Now, as long as the input of the op-amp is being driven with a relatively moderate or low impedance, then typically the input-referred voltage noise dominates. And we've already seen that for single-stage op-amps, such as the folded cascode, a large portion of Vn squared is determined by the input pair transistor's thermal noise. So again, we can make a simplifying assumption here that thermal noise of the op-amp, if properly designed, will be dominated by the input pair transistor's thermal noise 2 times 4 kT gamma over GM of the input pair transistors. Again, strong motivation to maximize the input pair transconductance. So using that model, we can do a noise analysis of op-amp circuits with feedback. Here's an example of a simple unity gain buffer. The op-amp shown here would have noise sources inside of it, but we can model it with a noiseless op-amp and our input referred voltage noise source, as shown here. Now, since the positive terminal of the op-amp is connected directly to ground, we can assume that ground is a very small source impedance, and therefore we only need to include the input referred noise model for the op-amp. Since the unigain buffer, we see right away that the output noise is simply equal to the input referred noise of this stage. And next, let's do a noise analysis for a little more complicated op-amp circuit shown here on the left. This is actually serving as a low-pass filter, and the resistor R2 is connected in the positive terminal of the op-amp, perhaps to perform input bias current compensation. So the op-amp itself has a noise model that introduces noise sources Vn, In plus and In minus. And as well, we've got 3 resistors in the circuit, each of which has its own noise model, modeled as a noisy current source in the case of R1 and RF, and a voltage noise source Vn2 for resistor R2. Remember, those are equivalent noise models of resistors. And again, we have to perform the noise analysis of the circuit for each noise source in turn. So first, let's consider the noise analysis of these current sources, IN1, INF, and IN minus. And we consider these together all at once because they all look very much the same. They all may be considered currents flowing into this node. So they all have the same impact at the output. So again, to do this part of the analysis, we would set Vn2 and Vn to 0, so they can be replaced by short circuits. In plus is also not being considered right now, so it can be replaced with an open circuit. So essentially the equivalent circuit ends up being something like this. Here's RF, and here is the feedback capacitor CF. And any one of those noise currents can be considered like this. Okay, and so the output noise that results due to any one of these noise current sources is simply sees a gain of RF at low frequencies, and there's a low pass filter there with a time constant of RF CF. So we can apply this filter to each of the noise sources in turn. Since we deal with noise spectral densities, we should shape it by the magnitude response squared. Okay, so these would be taking the magnitude here. And we do each one in term and add them up in a sum of squares fashion. So the result is the expression shown at the top here. So that's the total output noise spectral density that arises due to all three of the circled noise current sources. So next we'll have to consider the other three noise sources that were set to 0 in this first part of the analysis. Next, we'll analyze the impact of all three noise sources in the positive op-amp terminal, circled here, while setting the noise sources that we just analyzed to 0. So that means all three of these current sources are replaced by open circuits. So the equivalent schematic that we would be analyzing would have VI grounded, and each one of those noise sources in the positive op-amp terminal can be modeled like this: some voltage noise source in series with R2. In the case of IN plus, then that too can be modeled as a voltage noise source simply by taking the Thevenin equivalent of IN plus in parallel with R2. So the analysis for all three of those sources would boil down to the circuit shown here on the left. The resulting output noise is then this voltage noise spectral density shaped by the frequency response of this op-amp circuit, which it turns out is 1 plus RF over R1 at DC, where we have a simple non-inverting configuration, but then there's a pole introduced at the feedback network's time constant, RF times CF. So we've got that magnitude response squared shaping the noise sources in the positive terminal of the op-amp. And we could perform a similar analysis for each of those three noise sources. We'd add up the resulting output referred noise in a sum of squares fashion, giving us this expression shown here. So this is the noise arising from the positive op-amp terminal noise sources. The previous slide showed the output noise resulting from the negative op-amp terminal noise sources. To get the total output noise, we would have to add up the results on both slides, again in a sum of squares fashion, to get the final total output noise. So finally, let's analyze an op-amp circuit with capacitive feedback. This is an important example, as this is the equivalent circuit that arises in many switch capacitor circuits, and also circuits that are designed to provide low noise amplification. Using capacitors in the feedback network mean that there's no resistors to add any extra thermal noise. So the only noise sources that need to be included in the analysis are those arising from the op-amp. So here we've adopted a noise model for the op-amp with only its input referred voltage noise source, VNEQ. And this should be fine since we can assume that the input is being driven with a voltage source with a relatively small source impedance. So now, assuming that the thermal noise of the op-amp is of most interest to us, and that would be the case if it's a fairly wide bandwidth amplifier circuit, then we've essentially got a white noise spectral density at VNEQ, and that is going to be amplified at the output so that the output noise spectral density we can sketch here would be equal to the white input referred noise, the NEQ F squared, times the gain of this stage, which we will call G0 squared. Now the DC gain of this stage is simply that of a non-inverting configuration, 1 plus C1 over C2. So at the output, we see that level of thermal noise, essentially the input referred thermal noise amplified by the gain of the feedback amplifier, up to the bandwidth of this feedback. And then if we assume a first order model for the op amp, which would be valid if the op amp is compensated to have a phase margin close to 90 degrees, then we would see a 20 dB per decade roll off after that. Now the bandwidth of this stage, let's call it 1 over 2 pi tau, which we've seen from our analysis of first order single stage op amps, is related to GM of the input pair transistors divided by C1 in the feedback network. So we'll get to that later. The total output noise in this case is obtained by integrating this output noise spectral density over all frequencies. Now, to do that, we take this low frequency value, G0 squared, times the white input referred noise spectral density. And if we assume that the op amp is properly designed, we've seen that that should be dominated by the input pair transistors, resulting in an input referred noise spectral density of 8 kT gamma over GM of the input pair transistors. And integrating that up to a bandwidth of 1 over 2 pi tau would give us an expression like this. That's what we would get integrating it just up to the 3 dB frequency if there was a brick wall there, but there's not a brick wall there. There's this extra little bit of area under the curve beyond the 3 dB frequency. And turns out to take that into account for a first order low pass response, we just need to include an extra factor of pi by 2 here. So this is a neat expression because you get a whole bunch of cancellation happening. You get the pi's cancel, and 8 divided by 4 becomes just 2 in the numerator, and you end up with the expression shown here. Relatively simple expression for the total output noise, RMS. Now, the term 1 over tau is the 3 dB bandwidth of the closed loop configuration, which, as I've said, we've previously seen is for a first or a single stage op amp approximately equal to GM of the input pair transistors divided by C1. So substituting this in for 1 over tau, and also recalling that G0 is 1 plus C1 over C2, and that's rewritten here in a little different form. And we can substitute this expression and this expression into the expression for output noise. And again, you end up with some cancellation happening. And specifically, you see that you have a GM in the numerator canceling the GM that appears in the denominator here. So the end result is just 2 kT gamma. Those are all just constants. And this final portion here, that depends only on the capacitor value sizes. Interestingly, there's no dependence on circuits inside the op amp itself because GM-in has been canceled. And this will be true as long as the op amp, again, is designed so that the input pair transistor's thermal noise dominates. So this is very interesting because it means that if we have a certain output noise voltage that we need to ensure, then right away, just from that, we can calculate the sizes of the capacitors in the feedback network. So that's exactly how we would design a single stage op amp circuit based on this feedback network to achieve certain targeted noise and gain specifications. The noise specification would, together with the technology constants, would it would give us one equation for the two unknowns, C1 and C2, and then the other um, equation for C1 and C2 is given by the DC gain specification. So between these two specifications, there's a unique set of values for C1 and C2 that will allow us to hit those values. Once we've calculated C1 and C2 to meet the noise and gain specifications, then we can go and figure out what GM we need in the OTA in order to achieve a targeted 3 dB bandwidth. We know the 3 dB bandwidth is approximately GM of the input pair transistors divided by C1. We've already calculated C1 based on the noise spec, and we can calculate GM of the input pair transistor. In fact, you can go even further with this quick back of the envelope design procedure and say, well, assuming I design the input pair properly to have a very small value of V effective, which is what I would do to help ensure that the input pair transistors noise dominates and to ensure that I have the lowest possible power consumption to meet the noise and bandwidth specifications. So doing that, then I can kind of assume that the current that I have to use in the input pair transistors in order to achieve the GM that I just calculated for the bandwidth spec here is going to be bounded by the expression for a subthreshold transistor's transconductance. Now, the tail current will probably have to be a little bit higher than that because I'm not going to bias that input pair transistor deep in subthreshold, but it's a rough estimate of the sort of minimum tail current that I need in the input pair transistor. And then finally, I can even sort of get a ballpark estimate for how much total bias current is going to be required in the op amp. For example, if I assume that the op amp is going to be a folded cascode stage, then I may assume that half of all the current is being used in the input pair transistors, the other half is being used in the output stage. I can play with that ratio a little bit during the design, but that will at least give me a rough estimate for the total op amp current consumption. And then once I have that, I can just multiply that by the supply voltage. And essentially, just knowing the noise spec, the gain required, and the bandwidth required from this op amp, I can very quickly put at least a bounding estimate on how much power consumption this op amp will have to consume. Now, of course, there will be other specifications in general that I have to meet, slew rate, offset, 1/f noise, and so on. But this quick procedure allows you to, first of all, obtain rough estimates for the op amp's design parameters, and also elucidates a lot of the trade-offs associated with designing for noise, bandwidth, and gain specifications.